All right. So welcome back, everybody. Thank you for coming back to the course. And as Mr. Nikhil said, that the course would be an interactive course, and we will walk you through the details of the quick uh, show and tell that is going to happen today. Uh, there is some technical problem that's happening with installation of a library, but don't worry about it. I'll actually show you uh, the outcomes that we can work on from the example set that I have from the website of that particular material. For GEMPI, GEMPI is unfortunately very finicky. My programs worked perfectly yesterday. Today, certain issues are happening. Never mind. All right. So we are going to start off with looking at the basics of data analysis and plotting. That is very important for any geoscientist to look at data and to kind of do some basic analysis. And I don't want to misrepresent, but these days, there is this big thing about machine learning, deep learning, and so on and so forth. And the moment you get into this concept of machine learning and deep learning, the first thing they show you is linear regression. Now, a few years back, before these buzzwords came along, uh, linear regression was thought to be just a statistical process that has been known for, I don't know, maybe 100, 150, 200 years, where you are actually looking to reduce the difference between the point and the probable line that represents the solution. But now that is part of what we call deep learning or these fancy terms. So we will touch upon some of that material, but in no way, shape, or form we are going to be teaching machine learning in this course. But some of the techniques, you will get some sprinkling of that. All right, so without any further ado, I will share with you a little. Oh, this won't show up here. I can show it. I have to show this to you on the screen. All right. So let's do a new share Excel. So what I'm showing you here is essentially some trace element analysis from an Italian volcano. And we have all these trace element analysis and major element analysis. We are not going to work with the major element at this point of time, but we are going to look at trace element analysis. And there are about, I don't know, 372 data points that are there that contain all the analysis of the different trace elements. Now, it so happens that additionally, there are some blank spaces, like you can see over here in the Excel, where that analysis for that particular trace element was either inconclusive, or there was none of it, or there was some software issue or whatever, and there are some blanks there. Now, in the course, we will talk about how we handle these blank spaces. I saw another one go by in lutetium here. So there are numerous such scenarios. Now, as a geologist, when you do any kind of analysis, you have to be careful as to how you are calculating the statistical parameters for this. All right. Now, switching back to the material for the course today, I'm going to use this Excel file to extract the data and do some analysis. So I'm going to open my thing. All right. So over here, what I have is a little bit of code. And again, we won't spend too much time on code again, because our goal is to kind of to show you what we will be showing in the main course. So I'm going to run this code essentially. So it's going to take a little bit of time to do all the fancy analysis it's supposed to do. And then, boom, there you are. You have your curves. So in this particular case, I have tried to plot the a linear regression between lanthanum and cerium. And so I have plotted all the data up. And what I've also done is I've also created the this particular program is actually giving you the equation of the straight line as well as the R square value. All right. So now you would say, well, where is the equation of the straight line? Well, it turns out this beta naught and beta 1, these are essentially the parameters that are in the y equals mx plus b thing. Now, how do we calculate all of this? How do we do all of this? Additionally, I've also plotted uranium versus scandium over here and tried to show you that the R square is pretty bad. Well, because the fit seems to be bad, although it looks that there is plenty of data, and this line should properly represent the regression line or the best fit equation of the best fit line. But it's not the case compared to what you see over here. Now, to kind of quickly show you, to generate those two plots, I had to import 4 different libraries. The first one is pandas, which essentially takes in your data and allows you to look at the data in a clear manner. The matplotlib data library is for plotting. The NumPy module or the library is for doing certain calculations. And the scipy.stats part is for statistical calculations. And in this particular program, since we are trying to calculate the linear regression, we have had to use that. So I'll quickly show you how we do these kinds of things. So I'll spend a little bit of time over here because that's the key part that I think we should focus on. And here I essentially show you a function called linregress, which is derived from the statistics library. See, this st.linregress comes from this scipy.stats library, where when you feed that method these two values, df.la means from the data frame, look for the lanthanum and the cerium, and make it go through a process that is recorded in linregress. And linregress then spits out 5 values. So now that's something typically newcomers kind of get surprised with. What do you mean? We learned that one function can give you 1 value. Well, that is not the case. You can have a function return multiple values. And so we have all these parameters that are coming out. And then what we do is put it on as an equation of a straight line. All right, where B0 is the intercept, which means beta 0 is the intercept, and beta 1 is the slope of the line. Okay, so if I go over here, this is my intercept, and this is the slope of the line. Okay, now this would make sense to you because 1 point, it's a positive slope. You can see this line between cerium and lanthanum is a positively sloping line. I guess I should have put these hyphens in there. Instead of hyphens, I should have put commas. Well, we can try and play around with those there. And obviously, you can see that this is a negative slope over here. So it's a negative 8.84. So you can draw all of these kinds of things. Now, nothing stops you from generating these plots, more than 1 plot. So I have done only 2 here, but nothing stops you from generating the equation of these binary plots for all pairs of this trace elements. Okay. Now, not that they would all be very useful, but you have the option of doing that. Well, smarter people than me would say, well, instead of plotting all of them, I would plot the pairs that I know tells me something. All right. So the cool part about all of this is any volcanic eruption data you have in that form in the Excel spreadsheet that I just showed you, you would never have to change your program ever again. All you have to ensure is that the Excel spreadsheet that the lab sends you is in the same format. That means the column names are the same, and that's it. That's all you need. And all you need to do in your program is run that program for that file in their specific folders, and then you get all the figures that you need. In the main course, I would obviously be showing you how I can save these figures. What if you want it to be just like one data, one plot, not five of them together, or if you want five of them together, or eight of them together, or seven of them together, and that would be your final figure for your report, your weekly meeting with your boss or advisor or whoever it is. For yourself, you can look at that. Now, the next thing that I'm going to show you is that question about the using integrate. Well, before I move on, any questions people have? Quick questions, of course, because we don't want to spend a lot of time. Am I going too fast, or can you understand things? A couple of yes, no's would help. Okay. All right. So moving on, then I want to show that how we can use numerical solutions to integration over here. So for this particular problem, I'm going to use this library called SciPy, and in SciPy there is a function called integrate, and in that integrate function we use the numerical method trapezium. It's the trapezium method. Now there are other methods as well. You could use any one of them. It doesn't matter. Okay, the choice is yours. So, for example, in this particular case, the first part is essentially looking at the density. So, if I do this plot, if I run this code, I see how the density of the Earth's interior changes. Now, where did I get that from? So, I had to generate some data which is from the PREM model, which is the preliminary Earth model. And I have taken some density value ranges for certain depths, and I have used that to generate this particular plot. And also, I have generated a what is called a sort of an array where I have these different depth ranges with their densities stored away. So when I actually try to calculate the pressure at any given depth, I can actually pick those values instead of going and looking it up physically. Okay. So now this is the distribution of acceleration due to gravity, and this is where all that calculus business comes in, and this is where we are using that. This line number 11. This is where we are actually showing you how the application of that particular integration method over here. Now, I guess I am going a little too fast, but you have to set certain things up. When you try to solve a problem in programming, remember the computer knows nothing of what you want to do. It understands nothing. You have to set it up. You have to generate other values before, which have to be replaced by calculations that you would actually perform. Okay, so actually you can see that I have generated some arrays that contain zeros, a bunch of zeros, and they are done intentionally because I have to then replace them as I go in and calculate, because that would be the easiest way of solving them. Okay. And so this is how the acceleration due to gravity is calculated. This is the integration part that is taken into account. And then if I run this, execute this code, you can see that I have another plot that I have generated for the distance from the Earth's center to versus the acceleration due to gravity. Or in other words, this would be the surface, this would be the center of the Earth. Okay. And then you can see that as we go inside, I'm sorry, I said that completely wrong. This 0 is the center of the Earth, it's 6400 is the surface of the Earth. And you can see that as, the acceleration due to gravity on the surface is 9.8, kind of remains constant. And as it starts to go into the mantle, it goes above 10 meter per second square and then starts to decrease. Okay. And then keeps on decreasing in this linear manner. Now, why is it decreasing in a linear manner? Again, that would be something we would address in the course itself, not here, because long story short, we have set it up that way. All right. And finally, how we calculate the pressure, where we put everything together, where we bring in the integration aspect over here, and then we use the densities that we have calculated from different parts. And here is the solution of how the pressure changes with depth. Okay. And you can see that it's no longer a straight line. All right. And again, this is the center of the Earth over here. And this is the center of the Earth over here. And this is the surface of the Earth. So obviously, at the surface of the Earth, there is no rock sitting on top. So the pressure is due to the lithostatic pressure is 0. And then as we go inside, things start to increase. I mean, what is the use of generating something like this? Well, very simply, if you are into any kind of petrological work, this kind of gives you a quick idea of, when you're talking about 30 GPa, 40 GPa, or, in experimental petrology, in metamorphic rocks, you are looking at that. You can immediately correlate a depth with that. So you can say, oh, okay. So if I'm talking about 80 GPa, it's probably around 2000 kilometers inside the Earth. Now, because we use the PREM model, this becomes a little more helpful than just, a graph that I made up with some made up numbers. All right. So this is what I wanted to show you as far as a quick introduction to how we can do some data analysis, some statistics, and generate a bunch of plots. A good practice for us earth scientists is always generating a plot of some sort. Okay. So now what I'm going to do is I am going to switch gears and show you some other things. So bear with me 1 second. Switch this off. Go over this. And I'm going to show this to you. All right. So now, one of the things that I said that we can generate some surfaces based on latitude, longitude, either depth or elevation data. Now we'll spend some time showing you several examples of that. So I want to show you one such example. And in this particular case, we will be using a library called PyVista. It's right here. And I'm going to show you one of the examples because the data is there. It is easier for me to show. Okay. So what I'll do is I'll run all the cells and it will generate some plots, and I'll show you the plots as they come along. Now, oftentimes, as you run things, Python will give you this blue, pink colored box, and it will say that that such and such class is deprecated. Okay. Now, when you see this pink colored box, don't worry. It's just Python warning you something is going to get changed in the future of that particular lab. Okay. But other than that, that's fine. If you get a red box with red letters, that's bad, which is what happened to me like 5 minutes before the class when I was making sure all my codes will run. I will still show that to you where I'm getting stuck. So you understand where errors happen. Now, what I have done here is I've taken some data from the Mount St. Helens. So I have some coordinates of the Mount St. Helens and their elevation data at those coordinates. Okay, so I have XYZ data. And that XYZ data, what I have done is I have kind of normalized that data, the elevation data, and multiplied it by 100 so I can show them a little more carefully. And then what I have done is I have set up uh, some values for certain colors. So you can choose your custom colors or you can choose whatever standard colors are provided. I'll show you both examples. Okay. And then what I have done is I have said, well, how can I correlate that color with the elevation? So this is the part where I have done that. I have said for the colors, the greater than 80 will be red, less than 80 will be gray, less than 55 will be yellow, and so on and so forth, and uh, uh, something like that. And then what I have done is asked it to plot it. Now, this is a problem, unfortunately, that happens once in a while. I believe this should not happen, but you can see that you actually get a topographic surface of Mount St. Helens, and you mean that's the Mount St. Helens. That's the part that blew out, and the contouring is not showing up for some reason. Let me rerun this code one more time. Let me rerun this code. This happened to me yesterday as well. When I first ran it, it didn't work. When I ran it again, it worked. Okay, let me edit. Clear all the output. And what I'll do is I'll restart the kernel. I'll restart the kernel. Okay. Now let me see if this works. Fine. Fine. That. 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 Not take this long. Okay. I'll Run all. Okay, so some problem is taking place, but this typically shows you a plot like, let me actually show you what the final plot would look like. Okay. So that's what the plot should look like. Now, for some reason on my computer, uh, there is some issue that is taking place right now where the color rendering is not happening. The calculations are all there, but for whatever reason, the color rendering is not happening. And you can then change all those color renderings as well. So hopefully, yeah, I am having the same issue of that the color is not getting uh, rendered properly. Anyway, but you can we can do this when we have a lot more time during the course itself. Okay. You can actually see how do I know that my numbers are coming up correctly? Well, the numbers are coming up correctly because you can see in this particular case, I've used another library called color set, and you can see that the gradients are being shown here. Okay. And as I change the different kind of uh, uh, lighting, I can kind of see different variations to kind of show you how the elevation is changing. All right. Okay. So let's try and look at the plot over line. Okay. So in this one, what I am trying to show you is that one of the things that we geologists all love looking at is the topographic profile. What is the topographic profile along any particular direction? Run all of these. Do the calculations. So the first example is how to show you, like you have a volume, you create a volume and then you draw a line of section and then you show how that things vary over there. Okay. So this is like a generic example, but if I do that same thing for the Mount St. Helens, so I've taken a flat image of that, but this image actually contains the elevation data, and this is the line of section I am interested in. And you can see again that in some instances this is working, some instances it does not work. You know, Python has its well, not Python, but these third-party libraries have their little quirks, unless these are very well maintained and things like that. So you can see that here is the Mount St. Helens caldera, and this is the uh, topographic profile for that as we go from A to B. A is over here at 0, and B is over here, which is at about 14,000 meters, and the height above sea level is such. Okay, and so along this line of section, this would be the topographic profile. Obviously, you can choose your line of section because you know what points you want to go from. So, for example, you know the points where you want to start the section and end the section are over here. All right, let's see the contouring. I think this was also giving me some trouble, but well, let's see. Keep our fingers crossed to show, see if that works. So I'm going to run all of these. Let's see what happens. Plot. Okay. So this is, oh, now it's working. That's great. So what I have done is, again, generated a little mesh. And from the mesh, I'm generating some contours. Now, you might say, but why are you using all these things? I could do this in NumPy. Absolutely, you can. There is more, the third-party libraries are just there to help you and give you more solutions. Okay? But typically, you could write all of this from scratch if you want to and if you so desire. Okay, so this is essentially a contour line of a surface. You can generate isosurfaces as well. Again, we will talk about those much later. Then you can create banded contour intervals and kind of show which way certain points on that surface are pointing, because visualization is a major issue with people. Not everybody can visualize in 3D, because if let's go back to the first image, it's very hard for some people to figure out what is the slope along this region. Okay, so what you can do is generate these kinds of plots that tells the person that this vector points towards it's called a surface normal. So it tells you which way that particular surface in 3D space is pointing towards. The normal is pointing towards, which tells you which way the surface is sloping from. So I'm glad that this particular code actually ran. Now let's see terrain mesh if this one works. Time. Let's see here. Let's run all the cells and see if the Python gods are favor us today. And so what in this particular example, what we are doing is we have downloaded a gridded DEM. So we are downloading a gridded topographic surface. And then you can see the data that is there in that gridded DEM. So what is there? There are about 1.6 million cells and about 1.68 million points. And then what we have done is we have arbitrarily figured out the X bound, the Y bound, and the Z bound. Okay. And certain dimensions are provided. And the DEM in itself is two-dimensional, but it contains internally it contains the Z bounds, and we are going to use that. So what we have done is we have extracted a subset and we have created a little DEM of that area. Okay. So now, because we have that DEM and the 3Z thing is available, we have now generated or rather brought in what are the Z values over here. In fact, if you look at my scale, you will see this 1.44 e to the plus 3 is where my Z bound starts, or which is the minimum value for the clipped region. And the maximum value over that area is 2.769. Over here, you can see 2.77 e to the plus 3. Okay, so that Z value is there. Don't worry. You might say, well, there is nothing here. Well, no, that's not the case. The data is there. And then if you want to do look at the plot, so if we want to now look at the terrain plot, so we are actually projecting the z values to their appropriate distances, and you can generate a nice little 3D DEM over here that you can look at. And then you can also generate these kinds of things. And the fun part about all of this is you can do this. You can play around with this. You can look at it from different parts, and you can see the mesh. You can immediately take a PNG from different, so you can do these screenshots. You can save this as HTML. You can toggle rulers on or off. So if you can, I can toggle the ruler on, then I can zoom out, and then I can see the things like that. Okay. So you can generate all these kinds of views, as you, if I may use the term, and kind of show what's going on. Okay. Again, I'm glad that this particular one worked out. All right. So this brings me to another aspect of this. And for that, I will have to do the process of switching off my Anaconda and restarting it, because I have to use a completely different environment in which I have installed another library called PyGMT. So actually, let me try if this can be done on the fly. If this can be done on the fly, then nothing beautiful than this. PyGMT. I might have to switch this off and then bring off. Okay. There. So this should be help me do that. Okay. Go there. Go there. And let's see. Let's look at the coastline first. So oftentimes, again, this is another visualization tool. So run all cells. Okay, and it's very easy to generate figures like this. Again, we will talk about how we generate these kinds of things. And then actually I can plot some points on top of that. These are actually the rivers and lakes that have been plotted over here. You can play around with the resolution as well. So the lower the resolution, the more straight lines you get. The better the resolution, you get all the nooks and crannies that's there. And then you can obviously plot in many different ways. Another example would be, let's see here, if this, I think this was the contour map that was not working, maybe. Let's see. Cells. Oh, now this one is working. You guys are fantastic. You are making things work that wasn't working for me 2 minutes ago. So this is another way of, you can actually download earth relief data. This is 10-meter resolution data that I have downloaded. And then I've clipped a certain part of that, and then generated these contours, and I've provided some contour values. And then I can put in some contour line settings and intervals to kind of generate the contour values. You can smoothen the contours as well. Then you can put a map boundary around it. Then you can color code based on the contour value. So this would be simply elevation. So what I have done here is taken the elevation and generated a color map. where the elevation, positive elevation is red, the bathymetry is blue. So essentially this tells you that this is a part of an island or a peninsula somewhere. Uh, we are running out of time rapidly, so let's see. The plot view. So we can also plot data points. This is possible as well, particularly earthquake data. So essentially, I'm going to show you some earthquake data around Japan, and then essentially how you can take the magnitude of the earthquake and plot that as a representation of a circle. The size of the circle represents the thing. So to just kind of give you an idea of what kind of data I have year, month, day, latitude, longitude, depth in kilometer, and magnitude. And then what I have over here is essentially a plot of those, the location of these earthquakes over here. And then finally, I believe this was the magnitudes. So which ones are the bigger magnitude earthquakes versus the small magnitude earthquakes? And then you might say, well, what if I can color code this to depth so that I can understand, are shallower earthquakes larger or shallower earthquakes smaller? And lo and behold, you can do that as well. So you can, color code the depth, and the radius of is telling you the the magnitude. Let's see the 3D perspective thing. Yes, this is the one that got stuck. But this gives us a good idea to kind of see where things actually work and where things don't work, and how to kind of know that. Again, you guys are fantastic. I don't get, you see, that thing went away. So you guys should all sign up for the course. Again, now, see, I have chosen the resolution as 10-meter data resolution. So what I'm trying to do is actually generate a DEM or a 3D surface. And so first what I have done is developed a gridded surface. Then I've put in some color. Now, the better my resolution, the less crude this little pixelation is. Okay, so this is the surface relief, and you can play around with the perspective as well. Over here, I believe we played around with the plane parameter sets the elevation and color of the plane. Yeah, so you can play around with those kinds of things. So again, the perspective has changed, and I've sort of added some contours as well. So this last thing that I want to show you before we have to sign off is with GEMPI, and this is where I am getting stuck into problems, but I am hoping Lady Luck will shine on us because you guys are here. And let's see if that works. All right. Right. Well, the first thing that I wanted to show you was how you can take, in this particular one, library, the beauty is you can take borehole data and then actually try to understand the three-dimensional geology. Now, this particular library, GEMPI, is very well known for its finickiness, that sometimes it works, sometimes it doesn't work. This worked like literally half an hour ago on my computer, but let's see if this works again. Okay, so I have this error, but long story short, what's going on is that when I extract some data, so there is some data over here where I have a bunch of boreholes. The boreholes actually give me the intersection of a contact at a given depth. And what this particular uh, library helps me do is interpolate the surface, contact surface, like for a bedding surface for a unit across boreholes. See, this is the part, the interpolation of the borehole for different surfaces. So what it does, let's say there are 5 surfaces you have encountered across multiple boreholes. So it will go one surface at a time from one borehole to another, to another, to another, and try to correlate and match them. Now, there are expensive geological modeling softwares called SARPAC, called K-Mine, called there is one by Sequent, a Leapfrog, and so on and so forth. They cost tens of thousands of dollars. Now, what is the difference between that and this? There are some challenges with GemPy that GemPy can't model all possible geological scenarios that those softwares can, because there are dedicated people sitting, geologists and mathematicians, sitting around a computer all day trying to find out all possible geological solutions from a given scenario and model it and put it in their libraries. Okay. GemPy is an independently run thing with volunteers whenever they have time trying to do things. Well, without any further ado, I'm going to run this and pray that your luck remains and we get this thing going. Yeah, so our luck unfortunately has run out. This particular library, so this red color error is bad error, like something bad has happened, and apparently it couldn't find this particular module. Well, I'm going to try and run the other files just to see if any one of them would work. If it does, then that's great. um, it doesn't, I'm sorry about it, but hopefully we can make it work during the actual course itself. uh, I don't understand. I mean, all of these work. So yeah, unfortunately, I couldn't show you this, but hopefully I've shown you enough 3D that that there are alternatives to do exactly that, which is why I showed you PyGMT. Originally, I had no plans of showing you PyGMT today, but since I was getting into this trouble, I thought might as well show them if this works. So yes, you can do those kinds of things. So that is essentially all I have for